Hi, welcome to this video on revision for electricity in the IGCSE course. We're going to go through a PowerPoint that I've found on the TES, the Times Educational Supplement website, which was really good, made by another teacher in some other place of the world. It's a place where teachers share resources and you can go there and download stuff. And it tends to be very helpful. So here is the first page of the PowerPoint, and I'm going to be referring back to this other page where I'm going to be scribbling stuff around as I talk about things, and then referring back to this presentation as we move on through the pages. This will be a few videos long, and it should cover all of the current and the mobile charge part of the electricity syllabus. So not so much the static charge, but the current, light bulb circuits, resistances, parallel circuits, series circuits, and all of that stuff. Okay, let me get rid of that. So in the first part I wanted to talk about these three things, which are circuit symbols, recognize what electric current is and remember what it is in terms of the flow of electrons, and look at the way that current behaves when it goes through series and parallel circuits. Okay, so the first thing to have a look at then is this here. You should be able to recognize these symbols. When you have just one of these guys, we call that a cell normally, and when you have a few of them together, then you have a battery. When you park cars like this, also you come with a car like this and you park like that, and all the cars are like this next side to side, you also say that you're parking in battery formation. So battery just means parallel and side by side. So this is a cell and that is a battery. That's a light bulb. You should be able to recognize. A resistor should look familiar to you also. The ammeter and the voltmeter are pretty easy to spot. The amp is the unit of the current, and voltmeter is the unit for voltage, potential difference, and EMF. That's a switch, closed switch and an open switch. It's kind of the opposite of doors, because the closed switch is the one that allows the current to go through and the open switch does not allow the current to go through. So that's the opposite of a door. The light dependent resistor, or LDR, is this one here. You can see the arrows coming down. Those are like, to represent the light, and the more light fall on the more light that falls on the resistor, the smaller the resistance gets. So for an LDR, a high amount of light falling on it means a low resistance, which means a high current can go through for a fixed potential difference across it. So it's not a very good drawing, but it looks something like that. There's a resistor inside of a circle and then the two arrows coming in for the light. That's an LDR, and that is used in lots of circuits for responding to the lighting conditions. For example, on a street lamp, if you have your street like this and you have lamps like that, then very often you have LDRs on the street lamps, so that when the lighting conditions out here change, then the resistance of those sensors change, and then they can be used to activate a circuit to turn on or turn off, depending on whether there's a lot of light from the sun shining onto it or not. So you can use these light dependent resistors as sensors for noticing what's going on in the environment and responding to it, activating another circuit, and getting saving yourself having to do it manually, basically, or having a set time. If you have all your lights to switch on at 9 PM every night, but then in the summer it gets dark at 11 PM, then you've just wasted 2 hours of electricity. But if it does it automatically responding to the lighting, then you don't have to be changing those timings continuously. The thermistor changes in its resistance according to temperature. So that's the symbol of the normal resistor, and the thermistor looks like that. And these change according to temperature, so that can be used in thermostat in your house depending on the temperature of your house, of the air in your house, it will either switch on or switch off a heater or an air conditioner, for example. The resistance of that changes, and as the temperature goes up and you heat it up, the resistance goes down in a thermistor, which is the opposite of normal conductors. In normal conductors, if you heat them up, the resistance also goes up, which means that the current going through gets smaller, right? So if the temperature goes up in a normal conductor, the resistance goes up, and then the current goes down for a fixed potential difference. But in a thermistor, they're quite special. When you heat them up, larger temperature means lower resistance, so then you get a bigger current. That's because of the energy, thermal energy goes into the material in a special kind of way that you study at university, not even in A-level. They look at this, and a lot of electrons become free to carry electricity from one place to the other, and therefore it becomes a better conductor, and the resistance goes down. Okay, so this would be for a normal conductor. That's what happens when you heat it up. The atoms move around like crazy, and they don't let the electrons go through as easily, so the resistance goes up, and therefore the current goes down. And in these, it's the opposite way around. Variable resistor is just a resistor with a knob on it that you can turn, a dial you can turn up or down and increase or decrease the resistance. And the fuse is a safety mechanism that you should know about, made of a very thin piece of metal which melts when the current through it is above a certain value. You can have 3 amp ohms, 12 amp ohms, 13 amp ohms, 7 amp. You get them in 3 sizes, and the metal basically is very, very thin, so you have this normal wire coming along, and then suddenly you have this very thin wire, and then it continues like that, and this fuse will melt and break the circuit if the current is above a certain value, and therefore it will protect your appliance from being damaged if the current if there's a peak or a surge in the current. Okay, but it doesn't protect the person, because person needs an earth wire for protection. This protects the appliance. So they're called fuses, and it's just like a resistor, but it's got a little line through it. Alright, so those are the main symbols you need to know. This is the difference between a series circuit and a parallel circuit. Basically, if you are in a series circuit, there's only one route for the electrons to take. So if you waited for the current, the electrons actually, the current goes from long side to short side, so from positive to negative, but the electrons are actually going the other way, as you should know. But if you let the electrons get all the way through the circuit, and then you ask them before they come back to the battery, you ask them, hey, which way did you go? Then in series there's only one way they could have gone, so they're going to look at you and say, well, this is a series circuit, what kind of a question is that? But if you're in a parallel circuit and the electrons get home, and you ask them which way did you go, then they will have to say, well, I went through the first branch, or I went through the second branch. And that is a parallel circuit when there's 2 or more alternatives for the electrons to move through. You can have as many branches as you want here, and this can be as long as you want in the series circuit, but it can be long, but not with more than one branch. Okay, so let's have a look at atoms just very briefly to remember what's happening here. Here's a normal can of aluminium, and they focus onto the atoms, and they focus again, they zoom into the atoms, and they zoom in again, and they look at an atom which has protons and neutrons tightly bound in the nucleus. Very small nucleus. This is out of proportion, but really a nucleus is tiny compared to the orbit of the electrons. We said something like a pea in a football field, the electrons being outside on the sidelines. The electrons are, as they're so far away from the center of the atom, they're relatively easy to transfer from one place to another. So when we talk about static charge building up in places, or when we talk about conduction of electricity, that's all done by the electrons. It's not done by the protons, which are tightly bound in the atoms, and they don't move around very much at all. Right? If I put a current through this can, the electrons are going to be carrying the current. The protons are stuck to the neutrons in the nucleus of the atoms here, and they don't move around at all. They're vibrating around fixed positions. So that's very important that you see that the charge generally comes from electrons when you're moving, or you're talking about current in circuits. Okay, so let's move to the next little slide. It says electrons flow around in circuits. They gain energy from the cell and they transfer the energy to other components. Right, so when you see a light bulb like this and it's shining, it's getting its energy from the electrons, which at the same time are getting the electrons from the battery, getting the energy from the battery. That should be common sense. Let's have a look at the ammeter. They're used to measure current, okay, and we normally put them in series, which means that you connect them like that, not as a separate branch, but as part of the one loop for the electrons. The electrons are coming, the current goes this way, right? The electrons go the other way, so the electrons go like this, they go through the bulb, and then they go through the ammeter and out again, and then this way and all the way there. So the electrons only have one loop here, one option to go through, and therefore we've connected this ammeter in series, which is what you have to do, because an ammeter measures current, and if you imagine this is a river and you want to measure how much water is passing per second, then to measure that, the best thing to do is to have some kind of net like this in one point of the river and measure how much is going through, how much liquid goes through every second. And so you can measure it at one point in the river with no problem at all, and that is what an ammeter essentially does with electricity. So we always connect ammeters in series because they measure the current going through them. Okay, and that's different. The reason why we emphasize this is because the situation is different with voltmeters. Okay, so what's happening here? It's easy to determine what the value of the current is when you're in a series circuit, because the same as with if you assume that in a river the water doesn't spill out or anything, then if you ask somebody, hey, how much water is going through here, and then a little bit further you ask them how much water is going through here, then as long as there's no changes or new additions of water coming in from the sides or water leaving the river, then you can say that the same amount of current of water is going through here and through here. And therefore in a series circuit the same amount of current would flow through this point as through this point and through that point. And therefore an ammeter here and an ammeter here would both read 1 amp, the same as it's reading here. However, in a parallel circuit, situation is different. Now the water or the current can flow in different branches. So here the current is 4 amps, right? And now we're going to stop talking about electrons and we'll talk about the current as it's conventionally understood, which goes from positive to negative. And here the current is 4 amps, and as soon as it reaches here, the current's going to divide. Okay, it's going to divide, and it will divide in different proportions depending on the resistance of each branch. We've talked about this already. Hopefully you can remember that when the current comes to a point where the circuit divides in two, then what's gonna determine which way the current goes is the relative resistance. So one of the branches might have more resistance than the other, meaning that it will be harder for the current to go through. So if you imagine this one is full of some substance which is not letting it go through very well, and the water's coming through here, when it gets to this point, some of it will go through here, but more will go through the channel where it has least resistance. Similarly here, the same will happen when the current gets to this point. But if these two bulbs are identical, they both have the same resistance, and we assume the wires have very little resistance compared to the bulbs, that's what we normally do, so we ignore the resistance of the wires, then these being the same in resistance, the current is going to split equally, so that A1 and A2, each one reads 2 amps, adding up to the 4. And when they get here, they both recombine again. This current plus that current recombines, and at this point you would get again a reading of 4 amps, which is what you had here at the beginning, right? 4, 2, 2, and then 4 again. And this is in a parallel circuit. What about here? Well, this is the same principle. except you have to try to understand that somehow current is very intelligent, charge is intelligent in a way that's clever, or nature is, because it doesn't divide here in two and then here again in two as if it was later. It kind of already knows when it divides here, it already knows that there are 3 branches involved, and it divides accordingly. So this is 6 amps and these 3 are equal bulbs. This one goes with 2, this one goes with 2 amps, and this one goes with 2, all adding up to 6, and by the time they get back here again, they've all recombined and you have 6 amps here also. That's because all of these have the same resistance. If they didn't, then the split wouldn't be so easy. There are ways of calculating that though. We've talked about a couple, and we might have time to go into details of that in a later video. Okay, so what's happening here? Now we start to understand a little bit better what's happening, because we have a parallel circuit, two branches for the current to go through. There's 3 amps of current here, and here it's going to divide, right? How is it going to divide? Well, there's 1 light bulb here and 2 light bulbs there. Each light bulb has a certain amount of resistance, and if we assume that this and that and this have the same resistance, then you can see hopefully that there is 2 times the resistance here compared with that one, meaning that it's twice as difficult for the current to go through here as it is through this guy, meaning that the current here ought to be twice as much as the current here, because it's twice as difficult for it to go through here. So this is 3 amps. We need to divide it in 3 equal parts. So we say 3 amps, we need to divide them in 3 equal parts. That's 1 amp for each part, right? In normal mathematical ratios. And we need one of the branches to have 2 parts and one of the branches to, one of the branches to have 1 part and one of the branches to have 2 parts, right? There's going to be 2 parts of current going through the easier route. So how do we make up 2 and 1 with 3 amps? Well, we have 2 amps going through one of them and 1 amp going through the other, right? Together they make 3, and it fulfills the condition that one of them is twice as big as the other. So here we would have 2 amps going through and being measured here with the ammeter. 2 amps would go through there, and only 1 amp would go through this one, because it's twice as hard for it to go through. Here they recombine, and again here you have the 3 amps. Hopefully that makes sense. And this discussion is made a little bit simpler by the fact that all these resistors have the same, all these bulbs have the same resistance. When the situation gets a little bit more complicated, then you have to do some equations and calculations using V is equal to IR, and having a look at the potential difference drop through each one, and then doing the ratios for the resistance, and they're finding the current, how much goes through each one that way. But when they're equal, you can use this logic that I just said, that twice as many light bulbs is twice the resistance, so that will be half the current as in the other branch. In series circuits, this is much easier. All the currents are all the same throughout the whole circuit. Okay, so this is the first video that I wanted to make on a brief revision on this topic, and I'll go on to the next part in the second video coming up now. See you soon.